everybody, welcome back. I feel like it's been a while since I've recorded something for you. So since we're getting launching into working in ArcMap, I wanted to start going over with you a little bit more in detail about some of the information going into the software we're going to be using, also a little history of ArcMap and developing of GIS. So let's get started. So to start, I want to talk about, see if I can get this out of the way, what a GIS is. I know we've already been going over this quite a bit. It's kind of one of the points of the class. GIS stands for Geographic Information System. And as you are probably already aware, or maybe not, an information system isn't just a computer system, because oftentimes when we say that today, that's what we mean. It's something involving computers. But an information system is actually anything that helps contain and make order of a large amount of information. And when we're talking about maps as information systems have been around through human history. So I just wanted to show some images of early maps. This one on the left here is the earliest known map. It's called the Babylonian Imago Mundi from around 600 BC, and it's clearly carved on a stone tablet, and it shows Babylon as the center of the universe and things radiating out from there. These maps over here I just chose those because I thought they were interesting looking. I don't know too many details, but I know this Hereford Mappa Mundi, for instance, when we talk about the information maps contain, it's not just about what we actually, just where place things are, but it says a lot about the author of the map and the time they were living in. This is a map that was drawn somewhere in England, but it puts Jerusalem at the center of the universe, center of the world, and it has England all the way up here on the upper left, which is accurate, but apparently, according to what I read about it, it has Africa and Europe mislabeled, so that's interesting. And over here we have a map that comes from Korea from around 1402, and I love this map because I just think it's a fantastic conception of the world for them. Korea is quite large. China is large, but Korea kind of, pushes its weight there. But then over here we have Europe. I mean, isn't that interesting? You can kind of see something's going on here with Africa. Maybe there's the Arabian Peninsula there. And we have Europe, just kind of, something going on. So anyway, these are still information systems. After it was determined that the world was round and people started accepting that more, the mathematicians got to work. And as we discussed in week 2 of our class, people started to come up with things like geographic coordinate systems and datums and latitude and longitude. And we start getting these maps here that look a lot more familiar to us. Still geographic information systems, but now they actually have some math behind them. And they become a lot more analyzable and usable. So over time, as these things go, there was a change in thinking. It ceased to be just about a flat single map and more about layers. So people came up with the idea of actually creating different kinds of, mapping different kinds of information about the same place on different maps and putting them on top of each other to see where things would overlap and overlay. And people would actually draw maps out on like onion skin paper so they could lay things over and actually do layering and see things through. Sort of parallel to this is the advent of computers. And as we know, computers are kind of critical nowadays to how we would do GIS. And with that computer system, it just took, it was just a matter of time before people realized that they could take all this data with all these coordinate systems and put it into a computer. Of course, a little more difficult than my simplification, but I think you get the point. So fast forward a little bit, it's the 1960s. British researcher Dr. Roger Tomlinson is working for the Canadian Aerial Survey Company, and he had a brilliant insight. He thought, why don't we do this? Why don't we put all this geographic information, all of these photos that I'm taking, all these drawings that we do, and put it into a computer? And he came up with the Canada Geographic Information System. So very quickly, things filtered down into the hallowed halls of Harvard, where there were a variety of people examining this new software style or approach, but the person in particular we're going to focus on is Jack Dangermond. He was a student at the Harvard School of Design, and he was studying, I think, landscaping or landscape architecture. And he's the one who decided that he could use this GIS to help him in his business and his working life. And he primarily initially used it for that kind of design, that exterior sort of landscape design. But he just went on from there. You're probably aware, Esri is what the software we're using. It's probably the absolute leader, industry leader in this map making and software. And it's actually still one of the largest privately owned companies in the country, based out of Redlands, California. So not so far from here. So what makes a GIS? Again, a little review, but let's bring these points home. So absolutely, we need powerful computers. And again, as we've discussed actually just over the last couple weeks, computers are even more, it's more than just looking at this computer that's sitting on your desk. It's the remote servers that we have access to that are storing all this vast amount of information, but also processing it for us. So this is really important to our contemporary GIS system. We also have software that's always changing and advancing. The technology is also ever changing and advancing. So there's just a lot of opportunity for growth. And that means that we can always be doing new things. Of course, massive amounts of geospatial data. We know all about that now. So much of it out there. And this to me is the most critical part. I mean, of course, computers are important, but what about the human computer? It's the human brain. It's the insight and the analysis and the questions that the human brain asks of the computer system that makes the GIS do what it can actually do. There's this funny saying that says computers are stupid because they'll do exactly what you tell them to. So when you think about it, if something's going wrong with the computer, sometimes it's user error. It's not the computer. You told it to do that. Not necessarily that simple, but the capacity for human analysis and problem solving is very important in this whole equation. So from here on out, I'm going to start talking about what goes into map making in a GIS. I just would like to note quickly that there are several types of GIS systems out there. We're focusing and using exclusively ArcMap, but there are others. They operate under the same fundamental principles. Some of the interface is different, but these concepts here that we're going to discuss in the next couple of slides apply across the board. So one of the most fundamental aspects of map making is your coordinate system. This is why we brought it up right away, and this is why it's going to keep coming up. If you stick with GIS, this is going to underlie everything you do. Having a known coordinate system is how the software knows where to place things, and as you're dealing with multiple layers of information, maybe that are coming from different sources, you need to be able to reproject if something's not in the same coordinate system, and you need to know when to do that. So these are all it's vital to know the difference, it's vital to know how to use it, and for now, it's just important to know that it exists and that it's something that matters. So these other two elements here, non-geospatial data and geospatial data, we've talked a lot about already. You guys know what geospatial data is. Maybe you're not as familiar with non-geospatial. We have talked about it a lot, maybe indirectly. But let me first touch on this. So non-geospatial data is what gives the geospatial data for me, it's real analytical meaning. It gives it its meat. Non-geospatial data is also called tabular or attribute data. Tabular because it's on a table, and attribute because that's what it's considered. It's considered an attribute or a feature of the geospatial data. So just to give you an example, in this little image here, we have this square, also called a polygon. And this blue row here represents this polygon. So this polygon has a known location. It has a coordinate system. It has an actual point. You could find it on a map. It's projected onto a map, of course. And these sides actually all have real world lengths and measurements. So on this, somewhere on here, it's going to actually say what the size of this polygon is. But what else that's important to note about this polygon is, and this isn't necessarily in this table, But the information that could be here, in addition to that locational information, is what else is happening here. We could know, perhaps, identify if it's agricultural land, what kind of crops are being grown. If it's census data, we could find out what's the population, how many people live here. And if it's also census data, it could be just a parcel size or a different zoning code. So there's a lot of stuff that can be going on and attached to this as non-geospatial data that you find in this attribute table. So moving on to geospatial data. I know you guys know what this is. This is something that is clearly sort of the whole part of the whole point of this course. But I want to go down, introduce you now to how geospatial data is referred to as. Geospatial data comes in two types. It comes in vector data and raster data. So both of these kinds of data represent an object, place, or phenomenon with a known location, but they do it in different ways. So vector data consists of points, lines, and polygons, and raster data, which is always imagery, consists of cells. So I know you guys are familiar with this. We kind of did this back in week 4 through 7, where we discussed satellite imagery and brightness values and color guns and all that stuff. This is where it comes to play. It's with raster data. And just so you know, I don't know if it's kind of an old-fashioned, maybe it's a little old-fashioned now, but when I was younger and working on computers and personal computing was still relatively new, there was a lot of what was called vector images. And after getting into GIS, I realized that what that meant is they were images that were sort of drawn using points, lines, and polygons. So just like discrete images. And that's in opposition to raster data, which is essentially photography or photographs or imagery. So that gives you another little context for thinking about that. So let's dig a little bit more into vector data and raster data here. So like I said, the point, line, and polygon, also known as geometries, you'll hear that often. Let's talk about what is the geometry of something, what is it, and what people are referring to are saying, is it a point, is it a line, or is it a polygon? Now each of these different kinds of shapes or vector data points can have an attribute, or they definitely have an attribute table, but it'll have attribute information, that non-geospatial data, on that table. And that non-geospatial data can be a text, just text, like a description of something. It can be nominal, just a number, ordinal, it can be ranking, interval, it can be showing things like temperature, or it can be showing ratio, things that are like 3:1, or certain distances along a road. All of that is visible on the attribute table. And every time and we'll see this when you get into ArcMap, but every single one of these layers has its own attribute table with all of this information contained within it. So over here with raster data, I'll introduce you to a new concept when thinking about raster data. It's also called continuous data. And what that means is, remember I talked about vector imagery being just a discrete picture. When we use that in opposition to raster data is continuous because it's not just one little thing. It's not just one little spot. Even though this is one little spot, this actually is just one spot of a whole range of something that's happening over a much larger area. So in this case, what we're probably seeing in this is landscape or land cover. And land cover doesn't stop. Land cover keeps going. Land cover is continuous over the whole entire globe, whether it's land or water. The surface coverage, whatever it is, doesn't stop. Whereas a house does. A house is discrete. A house is vector data. If you look down on it, a house actually would show up on raster data, and it would be categorized as something in particular. But you can't apply vector data principles as well to raster data. You can, but it's not going to have quite the same analytical end that you want it to have. So I'm just going to talk briefly about layers and databases. This is maybe, if you haven't gotten it all into your ArcMap stuff, it might seem a little premature. But just to give you some idea of where we're headed with this, all of these vector and raster files I just described, These are all what are called layers, and layers are what we work with in our workspace in ArcMap. And layer, literally on top of each other. We combine the information, we make things transparent, and we can see how things overlay. And this is how we come up with do our analysis in ArcMap. All of these layers are stored in something that is called a geodatabase. So these geodatabases contain files, of course, and these files are feature classes, feature data sets, and shapefiles. You don't have to remember all this right now. Again, this will come up as we're doing our reading and over the next few weeks, but know that geodatabase is specific to GIS. When you download data for your labs, you're going to download geodatabases. If you were to open it on your computer, it'll look like complete nonsense. But if you open it within ArcMap, it'll look a lot more clear and make more sense. And I'll show you a bit more of that when we do the tutorial. So I'm going to stop that here. That's just, again, a few concepts. I really encourage you to read the chapter and study some of the ideas and just get into the lab and start working with it. So I hope you enjoyed that, and I'll be back soon.